1.2 complex plane. So we should start with a definition to define what a complex plane is. So a complex plane is basically called a z-plane, right? Is called a z-plane. That's terminology, right? And this is the complex plane, right? You have your y-axis, you have your x-axis, and we usually denote the y-axis as the imaginary part of z, and x-axis as the real part of z, right? And we have a point that is xy, right? We can write it as xy, but we can also write it as AB, such that A is element of A is an element of the real part of z, and B is element of the imaginary part of z. Right? You have a z over here. That should suffice. So you have A and B, right? Or really, you can write it as perhaps like this: y, z, no, y and x, right? You have the point x, y. That is x, y, right? That is z, and such that z is equal to x plus yi, or perhaps I, y. That's more formal, right? And now we may define it as which contains the point x, y, such that x is x is the real component, and y is the imaginary component, right? So now we have our definition, and then we say then x is called the real axis, and y is called the imaginary right. So that's 2 lines for I think 7 lines in the textbook. Really, it's unconscionable. No, it's just really hard to read the textbook. Oh, that's why you have to take notes with me, right? Not a theorem. Define. So we will define a vector, right? Definition. Vector. Well, let's draw an image before we define it. Right. So you have your imaginary axis and x-axis. No, the real axis. That's what they call it. And you have a point z, right? That is equal to x plus I, y, right? And this is your vector, right? So you say your v is equal to, well, perhaps not v, perhaps z. Really, it's just the same thing. Sorry, I should write it in blue. Right. It's equal to x, y. Right. That's the vector, right? Now, let's formulate a formal definition for the vector. A complex number z equal to x plus I, y, right, can also be viewed as a vector. Two-dimensional vector. That is a vector whose initial point is the origin. Sorry. Maybe like this. Then I have to write very small, very tiny. Well, origin and whose terminal point is xy. There. So now we have another definition. Modulus. That's a U modulus. Right. The modulus of a complex number z equals to x plus iy is the real number only if you square it, right? Well, that is really the length, right? Really the length. Right? In linear algebra, they call it norm. Right? Norm. There. A norm of a vector, right? A length of or the length of z, the length of this number, right? Well, example. Well, we want to calculate the modulus, right? Modulus. So, well, z is equal to -3i, and we want to find z, right? The modulus. So, well, that is just use the definition. Square, that is 4, square -3, that is equal to 9, that is equal to 13 being squared, right? And if z is equal to, you see, -9i, really this is on the tablet, I don't need to conserve paper, maybe I just start another line, right? So this is -9i, right? And if we want to find z, which is we want to find -9i, right? Really that is just equal to 0 square of -9, that is 81, right? That's really just equal to 9, okay? And now let's get into some properties, right? So we have some properties over here. Theorem. Properties of modulus, right? Well, that is, well, first we have I don't like the format in the textbook, so I will rearrange it. So you have I. You have I. That's 2. Sorry. So that is the square of the modulus is equal to z conjugate, and this is my quarter c, right? We know that z square, we know that v square, that is equal to the inner product of itself, right? So this is very similar, right? The reason why you have to know this is just that why this is important is that you'll see a lot of these and the norms, really, these in quantum mechanics, right? You have this is your quantum mechanics. You have integral from, I think it's negative infinity to infinity of a complex function, right, of x, right, and that's square, right, that is square, really, sorry, square, right, dx, right, in complex analysis, no, in quantum mechanics, right, and this is equal to, really, just this, the star, that's a complex conjugate of a function, right? That is just some quantum mechanics for you. And let's say we have this. The corollary to the first one is that we'll square. What about you just square root it? Right? Take a square root of it. Sorry, that's improper language. And well, if you have these two, right, square root of z1, z2, right, that is if you would expand it, right, distribute it, right, and you have number 4, well, corollary to the first one, sorry, eraser, there. Sorry. Pen, right. That is z1, z2, there's no conjugate, sorry, I wrote it incorrectly, right, that is equal to z1 divided by z2, right, just divide it. Well, I think of this is equal to, well, the product of these two minus 1, right, that is equal to, sorry, well, the product can be written as z2 negative 1, that is equal to, or distributed, right, I think this is the proof, right, that is equal to, well, z1 z2, right, there, some proofs, distance, again, really, the distance between 2 points, right, theorem, the distance between 2 complex numbers is defined in this manner. Well, that's just basically the norm. No, the modulus of z2 minus z1. Right, that's you do the x component, right, and then you do y component, right. So some more remarks. We know that the distance between u and v, if you have taken linear algebra, which I do assume you did, right, this is equal to really the norm of u minus v, which is equal to, if you write it like this is, the norm is really, well, it doesn't really matter if you write one line or two line, but I wrote it in one line for a particular reason, because this is an absolute value, right? This is also equal to v minus u, which is equal to vu, distance between v and u, right? The distance between u and v is equal to distance between v and u, right? So really this also has a corollary, which is that z2 minus z1, that's also equal to z1 minus z2, right? Well, because they're being squared, it doesn't really matter how you place it. So really you can flip it around and you can do the proofs for that, but it's very similar. Right. Anyways, let's do example 2. Right. That was example 1. Example 2. Example 2. Well, describe the set of points z in the complex plane that satisfies. So we want to find. I think. Really just xy. A point of xy such that z is equal to z minus I, right? This is a very mathematical notation. You can really, in the textbook they use I think 6 lines to describe this. Let's do it. Right. So that is, well, how do we approach this? We know that z is equal to x plus y I, right? And if we want to find the modulus, that is equal to x modulus x, well, z is equal to modulus of x plus yi, right? Well, by the definition, right, that is equal to, if we square each of the components, right? So this is z, and now we want to find the modulus of negative I, right? Well, that is equal to, well, really just a plus bi minus I, right? That is equal to, if we would really group the like terms, that is factor in I, that is minus 1, right? So that gives us really just let's say x squared minus, well, x squared plus y minus 1 square, right? Let a equals to x, b equals to y, sorry, right? Now if you would square both sides, right, that is equal to x squared plus y squared, that's equal to x squared plus y squared, and y minus 1 square, right? And if you would multiply out, right, x squared plus y squared minus 2y plus 1, right? And well, you want to solve this equation. Well, very well. If you would subtract x squared y squared both sides, and that is equal to 0, equals to negative 2y plus 1, that is equal to negative, that is positive 2y plus 1, oh sorry, equals to 1, y is equal to 1/2, right? 1/2. So, well, if y is equal to 1/2, what about x, right? We don't know what x is. Well, really, if you would subtract all the y terms, right, you only want to calculate the x terms, right? So that is basically x equals to x, right? So the z that you're trying to find, right? The z, really, this z is really just, x is not constrained. It can be any number, really. So you have xy, really it can be any number, and you have 1 plus 1/2 I, right? That is, well, this is 1/2, right? This is the imaginary, this is the real, right? It's really every point along, this line, right? There. So there it is, right? And let's get into some identities, right? Well, theorem. The triangle identity, right? The triangle identity in the complex plane is defined in the following manner. Right? That is x less than x1 plus z1 z2, right? I trust you have done some proofs on this already, but what this is basically if you have this, right? Right, this is absolute value. Well, really the length of z1 and z2, right? It's greater than z1 of the product, right? Sorry, the sum, right? So this z2, z1, right? Why does this work? Because, well, something might already cancel over here, because you might have a positive and negative, right? And then the absolute value or the modulus really just takes that away, right? And it doesn't. It's already cancelled before you take the modulus, and really, if you just separate the terms and then you do the modulus, these terms haven't cancelled away. So really, it's longer, right? Right, and you also have this identity. We have corollary of it. Let's make an example, and then we say the general form, right? So we say example 3. You say, let's say, because z1 plus z2 is equal to z2 plus z1, right? How about we do our triangle identity? That's basically equal to z2 plus z1, right? And it still holds, right? It still holds. Really, that's just no, sorry. Let's do this way, right? Z1 is equal to z1, right? That is true. How about we add z2 and we minus z2, right? How about we do that? That's still z1, right? So how about we group this, right? Right? How about I say this is equal to z1 plus z2, right? You want to add negative z2, right? And, well, that implies basically you have z1, right? And that is also, so this is also z1, right? So you can do this. Very tricky, right? And then we say, well, isn't this like a triangle identity, right? Or we can really just break this into z1 plus z2, right? So this is what we did, right? Plus, only if we break it apart, right? There. So it took me some time to figure out what the textbook was trying to manifest. Now if we know that, well, let's prove this real quick. Yeah. Well, we want to prove this. Well, really this is equal to your x plus y squared, right? That's and then your this is z, right? You have negative z, that's equal to, well, you have negative x squared plus negative y squared. That is basically equal to x squared plus z squared, or that is equal to z, right? And then, well, let's say if we add them, right? If we add them, right? Really, that is just equal to, well, that is bigger than if you subtract it, right? Because we know, how would I prove this? So basically you can think of it like this. You have z1 plus z squared, right? And that is less than and equal to, well, the triangle identity says that really by this figure over here, right? Plus z2, right? This is true, we just proved it. And well, it's really, if you take one of the term and subtract it, right, it's really just logical. If how I do it. Oh, I see what's happening. Well, let's come back to this later, right? You have z1 plus z2, that is less than or equal to z1, right, plus z2, right? Or if you subtract z2 on both sides, really, that is just minus. That's really just minus z2, right? And then, but isn't this what we just proved up there, right? We just flipped the sign, right? Then with minus z2, minus z2, right? And then you can, right, see, you can use this, right? And then what if you subtract z2 again, right? Because this is it's really just this. Well, then that implies, well, really, if you would do z1, right, minus z2, then really it's just it is just because this is practically z1, right? And then if you add a z2 inside it, right, and that creates this identity, right? So, but that is of no significance. What you have to know is just that the triangle identity implies, z1 minus z2, right? This is what you have to know. Maybe like this, box it. And then now let's move on. Right, let's move on next one. We have, well, we know that this is true by one of our additive properties, right? And, well, what about we take the modulus of it? Right? Well, this is bigger than, see, z2 minus z1, right? Well, which is what we factor out a negative sign, right? Right? Well, this implies because they are equal, and this is big, and because this is bigger than this, we say this implies z1 plus z2 is greater than the absolute value of this, right? The absolute value of the subtraction between, or just z1 minus z2, the modulus of it, z1 minus z2. Right, the difference, sorry. Right, the difference. And then next, if we replace z2 by z1, we just proved it earlier, right? we have z1 plus z2 that is less than or equal to z1 plus absolute value, the modulus of negative z2, well, that is also equal to z1 plus z2, right? We just proved it there, right? And that implies z1 minus z2, right? That is less than, you see, z1 plus z2, right? So let's use red. So this is important. This is important, right? And I think this one is also important. And you also have this is important, right? This is from textbook. I just proved all of it, right? And now I think we can. Not yet. Well, just one more, really. Let's do it, and then we propose the generalized theorem, right? And we can write it in the second page. Right. Well, if we replace z2 with negative z2, right, we get right. If we replace this, then this is really just the modulus of z1 subtract z2, right? And now we can propose a generalized triangle identity, right? A theorem, triangle identity. Triangle identity. Right. The triangle identity extends to any finite sum of complex numbers. Right, that is z1 plus z2 plus z3 plus zn is less than or equal to z1 plus z2 plus z3 plus zn. Right, I think this is quite evident from the geometric perspective, really. Now, well, we can write this into, well, the absolute value of a finite sum of I equals to 1, I equals to 1 of zi, right, is less than or equal to if we take out the sums, right? No, if we put it in, right, of zi. There. Really. That is the generalized theorem. And that is example 4. Let's continue. Example 4. We have -1 over z to 4 minus 5z plus 1 if, so this is more abstract, modulus is equal to 2, right? So now we're trying to come up with some sort of inequality, right? Well, observe that -1, that the modulus of this is equal to 1, really, right? We recall the property that we can distribute the absolute value. The absolute value apply on real numbers, or just numbers, really, it is an absolute value, and when it's applied to a complex number, it is called the modulus, right? And well, we can define that m, right? M is any positive real number, really, because this is an absolute value or modulus, it has to be positive, right? Yeah. And well, we say that 1 over z to 4 power minus 4z plus 1, well, that is less than or equal to m, right? Well, let's simplify these. Let's simplify the modulus. Well, we know that, if we would factor out a negative sign, so our goal over here is really to break it into two components, right? So really we can just say this is equal to, we have 4 over here, maybe we want to factor out a negative sign, right? Negative sign, we have 5z minus 1, right? And that is greater than or equal to if we would combine, if we would really just put the modulus in there. Right. Or just recall this formula over here. Right. We have sum outside, right, of zi is less than equal to, if we would put the absolute value in there. So now over here we just apply the absolute value in there, really. No, actually we pulled it out, so that's why it's less than, right? Because you see over here, right? Well, then what do? You can say that, well, this minus 5z plus 1 is greater than, z4 minus the absolute value of 5z minus 1. Really, that is just equal to, if we distribute the absolute value in there, the modulus, right? So basically you want to shrink it, right? You want to make this into this, right? So next we apply over here modulus to the fourth power, modulus plus 1 bracket, right? Well, this is just equal to, well, absolute value of, really, you keep modulus 4 power minus 5 modulus, right? Distribute minus 1, right, is equal to, well, we know what this is, right? We can apply this. The clue, right, that's just 16 minus 10 minus 1 is equal to 5, right? And because this is 1 over it, right, this is basically, well, we may conclude, let's write it over here, let's conserve some space, right? Minus 5z plus 1, really it is as much as, right? This is less than or equal to 1/5, right? So this is our answer. And this is 1.2, okay?